Log on, tune in, find out. Another good idea from Cambridge.
Lingyun Qiu, if I pronounce it correctly. So from Purdue University, and the title of the talk is Lipschitz stability of an inverse problem for the Helmholtz equation.
Thank you. It's my pleasure to be here to talk about our recent work. I changed my title a little bit from the Schrodinger type to Helmholtz equation. I will explain that. This is a joint work with Elena Barretta and my advisor Martin de Hoop. Okay, so first part, introduction. Before I define the forward problem, I need to define what is the data. Here we use the directly to Neumann map as the data. The directly to Neumann map, this lambda q, we divide like, is a linear, actually is a linear operator, maps this boundary directly to information G to its Neumann information, du d mu over the boundary. So this is so-called boundary measurements. I will treat this as our data. And roughly speaking, this operator is the data, this directly to Neumann operator, you can think it's all possible pairs of the u restrict on the boundary and the du d mu on the boundary. And for this work, I let this q equals to negative omega square over cx square, and omega is a number, the frequency, and c is actually cx is variable velocity model. So the Helmholtz equation become a Schrodinger type equation. So the forward problem is defined like this, from Q to the corresponding directly to Neumann map, lambda Q. So the corresponding inverse problem is we will determine Q from given lambda Q. And we jump directly to the so-called partial date. The partial date, this is mathematical define for the definition of the partial date. It's a local directly to Neumann map. Actually, the same thing as the definition of the full data, the directly to Neumann maps. The only difference here is the G. We will not use all of the G. We only focus on those G have compact support, and that means G concentrate on this open portion of the boundary. So if this sigma is whole boundary d omega, then is this lambda q is just the directly to Neumann map, is the full data. But this sigma is the open portion of the boundary which we can access it. That means that where you put your receiver and source. So this is the partial date. Actually, our result applied to the partial date. Okay, stability. The first question is, what is stability? To my understanding, I think the stability is if you have two data, say lambda 1 and lambda 2, two different directly to Neumann map, then those two data are close. And how close are the velocity models? So this is our definition of the stability, roughly speaking. And why the stability is very important? Obvious reason is this stability will decide the accuracy, which is strongly related to the resolution. And a deeper result, I think, is the good stability. I mean, good stability here means like Lipschitz type stability and at least the Holder type stability. Will give you some convergence result of particular logarithm, like the Landweber iteration on some Newton type logarithm, and also give you will guarantee the fast convergence rate. So that's why we want to deal with it. We always want to get some good stability here. Okay, the Lipschitz stability. The Lipschitz type stability is something like this. This is two potential here, and this is the difference of just two data. Then they are in linear manner. So this is called Lipschitz type stability. Okay, some known results. In 1988, Alessandrini proved this logarithm type stability for the actually for some smooth potential here. So you can see here is a HS norm. That means this Q must belong to this space, and that means no discontinuity allowed. So even for smooth for those potential with higher regularity, the stability is not that good. This type of stability is ruinable for any, I think for any numerical logarithm, because you only get logarithm type. That means extremely slow if you only have those type stability. And you note here, this is HS, but here it is S minus 1. So even for potential with high regularity, you can only control them with lower regularity. This is a bigger space than this one. That means with lower regularity here. And the bad truth is in 2001, Mendick shows actually this above estimate is optimal up to the value of this exponential sigma here. So that's best we can get. So what we can do here? The open problem we want to touch is we want to find some a priori information on the potential Q, such that those kind of information make physical meaning. It's physical relevant, and is numerical feasible. And the third part is we want to use those information to get some good stability, at least the holder type, and of course we want some Lipschitz type stability. Okay, our main result. Those are the assumptions we put on the calculation domain omega, and its accessible part of the boundary sigma. Sigma here is the open portion of that. So this domain is open and bounded, and the volume of this domain is less or equals to A. This means the Lebesgue measure of this domain. And its boundary is of Lipschitz class with some constant R0 and L. Those constants R0, L, and A, they will show up in the stability constant. And here sigma is the open portion of d omega, which is accessible to us. And assumptions on this potential is easy to read, but very restrictive, actually. That's our first shot to touch this question here. It's piecewise constant. Inside each subdomain dg, it's just a constant. But we can make it complex, actually. Not only real number, it should be complex valued. Okay, some assumption on those dg. This is the subdomain. And this is the mathematical setting of those subdomains. And the first one is they are open, connected, and pairwise they are non-overlap. And the union of those subdomains is the whole domain omega. And this paragraph said that if you have for any subdomain dm, for example, say dm here, you can always find a path from this. The first one is d1, and sigma is part of its boundary. And you can always find a path from d1 to dm, such that each two neighbor subdomains like dk and dk plus 1, the interface, they share an interface. And this interface will contain a non-empty open portion, sigma k. Also have some Lipschitz class with the same constant as before. That means for any subdomain, you can always find a path to go to that subdomain. That you can prove something here. And the result is let qk k equals to 1 and 2 be two functions of the form. They are piecewise constant, like this form. And there exists a constant c such that the Lipschitz type stability holds, and this is the stability constant here. We want to highlight here is this stability constant is uniform and only depends on dimension, some geometry property of the boundary, and the Lebesgue measure of this domain omega, and capital N is the number of subdomains. So usually for a problem, I think the dimension is 2 or 3 is fixed, and for now we fix this R0 and L. And A is not that important. It's just value of those whole domain, and it's given, so we can say this one is fixed. But the capital N, the number of the subdomains, play a very important role here. For example, if you want to get more get higher resolution, you want to divide your subdomain into smaller pieces, then this N will increase. I want to highlight here this N because I will show later how this constant depend on N. Because I think this constant here also have strong relationship with the convergence radius of some logarithm, like the Newton-Tech Landau-Weber iteration. So roughly speaking, this constant will decide the convergence radius, which is very important for most of the logarithm. I just gave a very naive numerical example, and this is the domain omega, and inside each piece is the Q is just a constant, and I randomly choose some complex numbers actually. So the x-axis is the norm of Q1 minus Q2 is L infinity norm. Just take the maximal value of those constants, and the y-axis is operator norm of lambda 1, the corresponding directly to Neumann map lambda 1 minus lambda 2. So you can see here actually this will be the constant. This one, the bottom line is the constant. So even for this simple case, the constant is not very good actually, because this to be honest, this is a very U-post problem in general setting. So we cannot expect too good constant here. Yeah. Okay. As I mentioned, I will show exponential behavior of that constant C, and with respect to the dimension n. I use an example in this section to show this this exponential behavior here, and okay, I should say this is a Lipschitz type stability constant in that inequality, and K1 is just a constant only depend on the omega, like this ball, and other stuff is not depend on the dimension and the capital N, those kind of things. And this N is the dimension, usually it's fixed, and capital N is the number of subdomains here. So to this example, Q, the potential equals to 1. I only use the real value of the potential here. So Q equals to 1 outside the Q, the biggest Q. And inside the biggest Q is just some function belongs to 1 over 2 to 3 over 2. And inside its small cube, Q is just a constant. And when you divide those, you subdivide the biggest cube here into small pieces, into small cubes. You can divide them with more and more small cubes, and so the number of subdomains n will increase. So how this constant behavior, how this constant behave when this n increase. Here is the result. This constant will behave like this. So you can say it's exponentially. So two things I want to say about this result. The first one is we need to be very careful to refine our mesh when we use the finite element or finite difference or grid or something like that. Grid or mesh. If you because people always want to get better result, like higher resolution, so we want to use refine mesh or grid. But when you refine the mesh, actually this constant, this stability constant will increasing dramatically, and the result is the convergence radius will collapse, will go to 0 very fast. That means you have to get a very good starting model for some particular algorithm, like the Landweber iteration and some Newton type algorithm. You need to you need to start from your start point have to be very close to the true model. Then you can get a convergence. This is the first thing, and the second thing is actually this result, this behavior here, implies some resolution limit. You can interpret that inequality like this way. So this one will give you some resolution limit here. Okay, let the epsilon be the error of the measured date lambda measure. That means the lambda measure difference between lambda measure and the true data is less or equal, can be controlled by this epsilon. And we tolerate error of the inverted Q up to m times epsilon. M is a constant. Constant here. Yeah. If all the subdomains dj have the same volume R0 to power n, that means in the trivial case you have calculation domain like this, and you divide this calculation domain into, for example, if you use the finite difference and into small cubes, so which dj is you label those small cubes, and dj is just one of the small cubes, and each dj have the same volume R0 to power n. Then the number of subdomains is equals to A divided by R0 to power n. Remember, A is the volume of the calculation domain omega. So the capital N is just this number. And hence, from this result, this is the behavior we get estimate from below of this constant. From this estimate, we have this result. Just to plug in this one back to this inequality, then we get this one. R0 must be bigger than this constant. K1 is constant, show up in the previous inequality. And A here is the volume, and 4 times m is the constant here. So this means no detail smaller than this number could be detected. So this actually gives a resolution limit. But this is only for the noisy data. Okay, and some future works along this way. I think the most important thing is the second one, frequency dependence, because for this work we combine them together, like the frequency and the Cx, because Q equals to omega square over Cx square. But for the real case, usually we have multi-frequency data available. So actually for same Cx, we have a lot of frequency, and then the corresponding data available. So definitely we want to know what this frequency, how this frequency effect on the Lipschitz stability constant C. So frequency dependence, especially for the low frequency part, I think is very important. And we're also looking for some reasonable function basis for Qx. Here we use constant, piecewise constant as a basis of the potential Qx. And we also show that the number of subdomains, you can say is kind of the number of the bases, how many bases you use here. So when the number of bases you use increase, that stability constant increasing dramatically. That means bad, worse. And so we definitely want to use less basis function here. So maybe piecewise constant is one choice here. Maybe we have more reasonable choice, like I don't know right now, but maybe wavelet play some role here, or maybe some other candidate. But definitely we want to find more function basis, more than piecewise constant. And probably for different situation, we can have some different function basis to work on that. Okay, yeah. Thank you.
So we have plenty of time for questions. Yes.
Could you give us just a rough idea what you had to do to get a stability estimate like that? How close is it to the original arguments of Alessandrini and so on?
Sorry, what? Alessandrini?
Yeah, could you give us a rough idea of what techniques you used to prove that Lipschitz estimate? And how close it was to the original arguments of Alessandrini?
Yeah, well, we follow their method, Alessandrini's approach to the EIT problem, and we construct the same similar singular solution. But the trouble is for for lower dimension, like n equals to 2 and 3, the Alessandrini identity for the EIT problem is lambda 1 minus lambda 2 operate on U1, and the pair with U2 equals to the integral over gamma 1 minus gamma 2 times gradient of U1 dot gradient of U2. So actually it's not that smoothing. For example, they use the green function to construct this singular solution. That means U1 and U2 actually are green function, G1 and G2. So for example, dimension 3, the green function itself belongs to L2. So the right-hand side, that means the Q1, if we go back to this case, Q1 minus Q2 times G1 times G2 belongs to L2. But their technique is we have to study the asymptotic behavior when those 2 points when some point close to the interface. So the left-hand side of the Alessandrini identity will blow up with some singularity, some constant time. Actually, this constant is Q1, the norm of Q1 minus Q2, and times the R to some power. So it's singular. But the right-hand side is bounded. It's just some constant. So we cannot use that. So for the proof of this case, we choose some other candidate, like the first-order derivative, some first-order derivative, to replace the role of the green function. The first-order derivative of the green function to replace the role of the original one. And but the easier part is we have better result for the three-sphere inequality, which is very important to our proof. I don't want to go much detail about that. The proof is
Thank you.
very technical.
Thank you. Other questions?
So I'm not going to pretend I understand everything that's on your slides. I don't. So I'm going to ask what may be a very, very stupid question. So just when you show in one of your last slides, you show the difference. Okay? Your stability measure depends on the difference between the two lambda maps. Right?
You mean the mean result? This one?
Yes.
Yeah.
So stupid question. Where do those two lambda maps come? If I give you a bunch of data, and let's suppose I have, say, for acoustics, pressure and particle velocity on the boundary. So I might not know the medium parameters, I might not know the map, but I have the map because I have the two fields. But where do those two lambda come from?
Those two lambda from, you can think it's about, you can take here, so roughly speaking, this is the data, lambda. And you can think it's all possible pairs, like this way. This is the pressure, this is the first order derivative.
So I think his question was simply, you just got 2 lambdas and 2 q's. It's how close the data is. Tells you how close the solution is. That's all.
Okay. Sorry, I missed
sorry.
that. Like I said, stupid question.
How does your stability depend on the length of sigma?
Okay, is something related to the offside?
Well, I
Yeah.
expect the bigger is sigma, the better is the stability.
Go to constant here. Actually, the geometry, the length of the sigma related to this one, R0 and L. It's given these two constants describe the geometry property of this boundary, and the sigma is part of the boundary. So
Yeah, but how big it is? Because sigma could be half of the boundary or could be the whole boundary. So the more information you have, the better would be the stability, presumably.
I mean, sigma here is not just a plan, it's not flat. So the geometry of this sigma also play a role here. For example, if you have the same length, but it's bent like this way, and the constant will be different.
So the constant should depend on the measure of sigma somehow.
Yeah, and the measure of sigma and the geometry property of sigma contained in those two constants, R0 and L.
I thought R0 and L are related to the boundary d omega, not to the sigma.
But the sigma is part of the boundary. So actually, this sigma has the similar, have the same constant of this boundary.
I mean, I think that's only for uniqueness, not for stability.
If the sigma has some better property, like the better R0 and L, maybe you can get some.
No, I'm after whether sigma is the whole d omega.
When the sigma is whole d omega.
Yeah.
So suppose, for example, omega is a ball, and sigma is a hemispherical cap. How would your constant change if sigma were all of the boundary or just the cap?
Definitely, full data will have better stability,
Yeah,
but
that's what
I don't know how it depends on that. I mean, in terms of this R0 and L, I just know which one is better, but I don't know how. If that is the question.
Okay, thank you. Is there another question? Okay, so thank you again.